Welcome to another exciting episode of Database Internals Crashcasts. I'm your host, Sheila, and today we're diving deep into the world of column-oriented databases. Joining me as always is our database expert, Victor. Hi, Victor.
Hello, Sheila, and hello to all our listeners. I'm thrilled to be here to discuss this fascinating topic.
Great to have you, Victor. Today's episode is packed with information, so let me quickly outline what we'll be covering. We'll start with a brief history of column-oriented databases, then move on to their basic structure and advantages. We'll also explore their internal workings, query optimization, and real-world implementations. Finally, we'll discuss common misconceptions and best practices. But before we dive in, let's kick things off with our quiz question for the day. Listeners, here's your challenge. In a typical use case, which type of database would likely perform better for analytical queries on large datasets with few columns but many rows? A row-oriented database or a column-oriented database? Victor, any thoughts on this question without giving away the answer?
Oh, that's an excellent question, Sheila. It really gets to the heart of why different database architectures exist. I think our listeners will need to consider the nature of analytical queries and how data is typically accessed in such scenarios. It's a tricky one, but I'm excited to see what they come up with.
Indeed, it's not as straightforward as it might seem at first glance. We'll reveal the answer at the end of our episode. Now, let's start at the beginning. Victor, can you tell us about the history of column-oriented databases? Why were they created and how have they evolved?
Certainly, Sheila. Column-oriented databases have their roots in the need for more efficient analytical processing. They were conceived in the late 1970s, but it wasn't until the early 2000s that they gained significant traction. The primary motivation was to overcome the limitations of row-oriented databases in handling large-scale analytical workloads. Traditional row-oriented databases store data in rows, which is great for transactional processing, where you need to access all fields of a record at once. However, for analytical queries that often only need a few columns, but across many rows, this structure becomes inefficient. Column-oriented databases were developed to address this issue by storing each column separately. This design evolved over time, with improvements in compression techniques, query optimization, and integration with big data ecosystems.
That's fascinating, Victor. So, if I understand correctly, the main difference between row-oriented and column-oriented databases is how they physically store the data. Can you elaborate on this basic structure and why it makes a difference?
Absolutely, Sheila. You're on the right track. In a row-oriented database, all the data for a single record is stored together. Imagine a table as a book where each page is a complete record. In contrast, a column-oriented database is like having separate books for each column, where each book contains all the values for that specific attribute across all records. This fundamental difference in data organization has significant implications for how data is read and processed.
I see. So, if we have a table with customer information including name, age, and email in a row-oriented database, we'd store john30johnyemail.com together. But in a column-oriented database, we'd have all names in one place, all ages in another, and all emails in a third. Is that correct?
That's exactly right, Sheila. Your analogy is spot on. This structure gives column-oriented databases some distinct advantages, especially for analytical queries. For instance, if you wanted to calculate the average age of all customers, a column-oriented database would only need to read the age column, while a row-oriented database would have to scan through all the data, including names and emails, which aren't relevant to the query.
That makes a lot of sense. It seems like column-oriented databases would be particularly efficient for big data analytics. Are there any other significant advantages or use cases we should be aware of?
Absolutely, Sheila. The efficiency in analytical queries is indeed a major advantage, but there are several others. 1. Data compression. Since each column contains the same type of data, it's often more compressible than mixed data types in rows. 2. Parallelization. Operations on columns can be easily parallelized, improving query performance. 3. Late materialization. This is a query optimization technique where only the necessary columns are read and joined together at the last possible moment. 4. Faster data loading. In many cases, data can be loaded faster because each column can be written independently. As for use cases, column-oriented databases excel in scenarios involving data warehousing, business intelligence, and any situation where you need to analyze large volumes of data, especially when you're only interested in a subset of columns.
Those are some impressive advantages, Victor. I'm curious about the internal structure and data storage in column-oriented databases. How exactly is the data organized on disk, and how does this affect query processing?
Great question, Sheila. Internally, column-oriented databases organize data into what's often called column stores. Each column is stored as a separate file or set of files on disk. These files contain the values for that column across all rows, often sorted and divided into segments for efficient access. The columns are typically stored with metadata that includes information about the data type, encoding, and compression used. This metadata is crucial for query processing. When a query is executed, the database engine reads only the columns required for that query. It can skip entire columns that aren't needed, which is a significant performance boost for analytical queries that often only involve a subset of columns. Moreover, since each column contains homogeneous data, all of the same type, the database can use specialized compression techniques and encodings that are optimized for that data type. This not only saves storage space, but also reduces I/O during query execution.
That's really interesting, Victor. You mentioned query optimization earlier. Can you explain more about how column-oriented databases optimize queries, especially the concept of late materialization?
Certainly, Sheila. Query optimization in column-oriented databases is quite fascinating. Late materialization, which I mentioned earlier, is a key concept here. In traditional row-oriented databases, when a query is executed, entire rows are read from disk and then filtered based on the query conditions. This is called early materialization. In contrast, column-oriented databases use late materialization. Here's how it works. 1. First, the database reads only the columns needed for the query. 2. It then applies any filters or conditions on these columns. 3. Only after this filtering is done does it reconstruct the rows for the final result set. This approach can significantly reduce the amount of data that needs to be processed, especially for queries that filter out a large portion of the data. Another optimization technique is vectorized query execution. Instead of processing data one row at a time, column-oriented databases can process data in batches or vectors, which is more CPU efficient. Additionally, these databases often use advanced indexing techniques, like bitmap indexes, which are particularly effective for low cardinality data, often found in analytical workloads.
Wow, that's quite sophisticated. It sounds like there's a lot of thought put into making these databases as efficient as possible. You also mentioned compression earlier. Can you elaborate on the compression techniques used in column-oriented databases?
Absolutely, Sheila. Compression is a crucial aspect of column-oriented databases, and they use several clever techniques to minimize storage requirements and improve query performance. 1. Dictionary encoding. This is used for columns with low cardinality, few unique values. Each unique value is assigned a numeric ID, and the column stores these IDs instead of the actual values. This is particularly effective for things like status codes or categories. 2. Run length encoding, RLE. This works well for columns with many repeated consecutive values. Instead of storing the repeated values, it stores the value and the number of times it's repeated. 3. Delta encoding. This is effective for sorted numeric columns. Instead of storing the actual values, it stores the difference between consecutive values, which often requires fewer bits. 4. Bit packing. This technique uses the minimum number of bits required to represent the values in a column, rather than using a fixed number of bytes for each value. 5. Null suppression. This involves not storing null values explicitly, but rather using a separate bitmap to indicate which values are null. These compression techniques not only save storage space, but also reduce I/O during query execution, as less data needs to be read from disk. The choice of compression technique can vary from column to column based on the data characteristics.
That's fascinating, Victor. It's amazing how much thought goes into optimizing these databases. Now, I'm curious about real-world implementations. Can you give us some examples of popular column-oriented databases and how they're used in practice?
Of course, Sheila, there are several well-known column-oriented databases in use today. 1. Apache Cassandra. While primarily known as a NoSQL database, Cassandra uses a column family data model that shares some characteristics with column-oriented databases. It's used by companies like Netflix and Instagram for handling large-scale distributed data. 2. Google BigQuery. This is Google's fully managed serverless data warehouse that uses a columnar storage format. It's designed for fast SQL queries on large datasets and is popular for business intelligence and data analytics. 3. Amazon Redshift. This is Amazon's data warehousing solution, which uses a column-oriented approach. It's widely used for business intelligence and reporting in cloud environments. 4. ClickHouse, an open-source columnar DBMS developed by Yandex, known for its high performance in real-time data analytics. 5. Vertica, a commercial column-oriented database used by companies for high-performance analytics on large volumes of data. These databases are often used in scenarios involving large-scale data warehousing, real-time analytics, and business intelligence applications where fast query performance on large datasets is crucial.
That's a great overview, Victor. How do these column-oriented databases compare to other types of databases, like traditional row-oriented or key-value databases?
That's an excellent question, Sheila. The comparison really depends on the use case. Let's break it down. 1. Column-oriented versus row-oriented. Column-oriented excels at analytical queries on large datasets, especially when only a few columns are needed. Row-oriented is better for transactional workloads where entire records are frequently accessed or updated. 2. Column-oriented versus key-value. Column-oriented databases are optimized for complex queries and aggregations across many records. Key-value stores are simpler and typically faster for individual record lookups, but less suitable for complex analytics. 3. Column-oriented versus document databases. Column-oriented databases work well with structured data and predefined schemas. Document databases offer more flexibility with semi-structured or unstructured data, but may not perform as well for large-scale analytics. The choice between these depends on factors like the nature of your data, query patterns, scalability requirements, and the balance between read and write operations in your application.
That's really helpful, Victor. Now, I'm sure there are some common misconceptions about column-oriented databases. Can you highlight a few of these and explain why they're incorrect?
Certainly, Sheila. There are indeed several misconceptions about column-oriented databases. 1. Column-oriented databases are always faster. While they excel at certain types of queries, they're not universally faster. For OLTP workloads with many small, random reads and writes, row-oriented databases often perform better. 2. Column-oriented databases are only for big data. While they shine with large datasets, they can be effective for smaller analytical workloads too. It's more about the nature of the queries than the size of the data. 3. Column-oriented databases can't handle real-time data. Some people think these databases are only for batch processing, but many modern column-oriented databases support real-time inserts and updates. 4. Column-oriented databases don't support transactions. While it's true that many early column stores didn't support ACID transactions, many modern implementations do offer transactional capabilities. 5. Column-oriented databases are always the best choice for data warehouses. While they're often a good fit, the best choice depends on specific requirements, including query patterns, data volume, and update frequency. Understanding these misconceptions is crucial for making informed decisions about database architecture.
Those are great points, Victor. To wrap up our discussion, could you share some best practices or tips for working with column-oriented databases?
Absolutely, Sheila. Here are some key best practices. 1. Denormalize your data. Unlike in row-oriented databases, denormalization can improve query performance in column-oriented databases. 2. Optimize your schema. Group columns that are frequently queried together. 3. Use appropriate sorting keys. Sorting data can significantly improve compression and query performance. 4. Leverage materialized views. These can speed up common queries by pre-computing results. 5. Be mindful of write patterns. While these databases excel at reads, writes can be more challenging. Batch your writes when possible. 6. Use the right compression techniques. Choose compression methods based on your data characteristics and query patterns. 7. Regularly maintain your database. This includes tasks like reorganizing data and updating statistics to ensure optimal performance. 8. Monitor and tune query performance. Use the database's built-in tools to identify and optimize slow queries. Remember, these are general guidelines. The specific best practices can vary depending on the particular database system you're using.
Thank you, Victor. Those are really valuable tips. Before we wrap up, do you have any interesting or fun facts about column-oriented databases to share with our listeners?
Sure, Sheila. Here's an interesting fact. The concept of column-oriented storage actually predates relational databases. It was first proposed in 1969 by Morton Zloof at IBM, several years before Edgar Codd's seminal paper on relational databases. However, it took several decades for hardware to advance enough to make column-oriented databases practically viable for large-scale use. It's a great example of how sometimes ideas in computer science can be ahead of their time.
That is fascinating, Victor. It's always interesting to see how technology evolves over time. Now, let's reveal the answer to our quiz question. We asked, in a typical use case, which type of database would likely perform better for analytical queries on large datasets with few columns but many rows? A row-oriented database or a column-oriented database?
Yes, the quiz question. Based on what we've discussed today, the answer is that a column-oriented database would typically perform better in this scenario. Analytical queries on large datasets with few columns but many rows is precisely the kind of workload that column-oriented databases are optimized for. They can quickly access just the needed columns without having to read through all the data in each row.
Excellent. I hope our listeners were able to figure that out from our discussion. Now, let's summarize the key points we've covered today. 1. Column-oriented databases store data by column rather than by row, which is especially efficient for analytical queries. 2. They offer advantages in data compression, query optimization, and parallelization. 3. Column-oriented databases use sophisticated techniques like late materialization and vectorized query execution. 4. They employ various compression techniques like dictionary encoding and run-length encoding. 5. Real-world implementations include Apache Cassandra, Google BigQuery, and Amazon Redshift. 6. While excellent for analytical workloads, column-oriented databases aren't always the best choice for all scenarios. 7. Best practices include denormalizing data, optimizing schema design, and being mindful of write patterns. Victor, is there anything you'd like to add to this summary?
That's an excellent summary, Sheila. I'd just add that understanding the specific requirements of your use case is crucial in deciding whether a column-oriented database is the right choice. While they excel in many analytical scenarios, it's important to consider factors like write frequency, transaction requirements, and the nature of your queries when making architectural decisions.
Great point, Victor. Now, if we had more time, we could have delved deeper into topics like hybrid database systems that combine row and column storage, or the challenges of implementing ACID transactions in column-oriented databases. Perhaps we can cover these in future episodes. To our listeners, thank you for tuning in to another episode of Database Internals Crashcasts. If you enjoyed this episode, please don't forget to subscribe to our podcast and leave us a rating. Your support helps us continue to bring you in-depth explorations of database technologies. Until next time, keep querying.